So, dear colleagues, let us start our morning session. And it's my pleasure to introduce the first speaker of our conference, Meirav Topol. She is a permanent participant of our conference, and I'm very glad to see you and meet you once again. Meirav, please.
Thank you very much. So, hi, good morning, everyone. So my name is Meirav. I publish my works as Meirav Amram because that was my maiden name. I would like to tell you a bit about myself. First of all, I am an algebraic geometer, and I work a lot in classification of algebraic surfaces and curves. And of course, I use geometrical, topological, and algebraic methods. And lately, also some algorithms to proceed in my work. Except this, of course, I also study some algebraic curves such as line arrangements and conic line arrangements. And in the talk, I will show you some nice and good ideas, and I hope that you will like them. In the bottom of the first page, you can see my email. So for any suggestions, ideas, questions, you are welcome to write to me. I'm always available. I would like to thank the organizers for the wonderful platform to share with everyone the good ideas. And I would like also to dedicate my talk to the Ukrainian team and the organizers. As you can see with the colors along the talk, with the colors of the Ukrainian flag. And I want to tell you guys that you are very brave and very dedicated to have such a wonderful conference each year. So, as Sergey said, it's not the first time for me to participate in this amazing conference, and I'm very happy to be here again. It's a big pleasure. And I hope for you, I wish for you to have peace, and very soon I can come to visit you in your institute. This is my wish. And now I will start with my talk. I will speak about deformations, fundamental groups, and Zariski pairs in classification of algebraic curves and surfaces. So I will show you these 2 points of view. So first of all, the goal of the talk was all the time the classification of algebraic surfaces and curves. Also branch curves, which we get from algebraic surfaces. It's a very interesting and big question along the years. And fundamental groups, which I will speak about, are also very nice invariants of the classification. Now, I will start my talk with algebraic surfaces. We begin with an algebraic surface, S, in some projective space, and we project S onto the projective plane CP square. And then this is happening via a generic projection. And then we get the branch curve C in CP square. And C can tell us a lot about the surface S itself. For example, the type of the singularities, the degree, and many other properties that we can derive. Now, the interesting thing is the fundamental group G. This is the fundamental group of the complement of C in CP square. So it's a very nice invariant. And why? This is the reason. G does not change when the complex structure of S changes continuously. So this means that all the surfaces in the same component of the moduli space, they have the same homotopy type and therefore the same group G. So it's a very good invariant. But sometimes it is very difficult to draw the picture of the branch curve C. Okay, so to draw a picture, very difficult, but maybe later on we can get some properties about C. I don't want to draw a picture of C, too complicated. And I will suggest some good ideas of how to derive the presentation of G. Okay, now, some nice method in the classification First of all, you see that it's written in the title softwares. But before this, I want to tell you what we use in general, the mathematicians. So the methods that assist us in classification are, for example, topological classification, intersection theory, singularities, cohomology, symmetric groups, and so on. Each one does it in his own or in her own niche in the research. But if we want to use some algorithmic methods, at least from my side, we need to consider three parameters. The first parameter is the specific properties of the surface or the curve. The second parameter is the desired level of detail in the classification. And the third parameter is the preferences and needs of the researcher. Of course, to which resolution we want to arrive and what information we want to get about C or about the group G. So, of course, I will show it later on in the talk. So, mathematicians usually in the mathematical community, they use magma, singular, maple, and so on. In our research, we use usually magma, also SageMath, and some self-constructing software which were built with Sinichkin. Now, before I proceed to how we do all this, I just want to show you some works about the generations. What is a degeneration? You can see here in this diagram. If we start with an algebraic surface S and in some projective space, and we project S onto CP square with a generic projection, we will get a branch curve C. But it's too complicated. So we can go on the longer but safer way. We do the generation. This is to divide the surface to a union of planes. It is called S tilde. And then when we project S tilde onto CP square, we will get C tilde. This is the branch curve of the generated object. And then we can do the opposite process, which is called regeneration, in order to get or to recover the branch curve C. Again, I don't want to draw a picture of C, it's too complicated. So you can see here an example as a work with Tan, Xiu, and Yoshpe. This is, for example, S tilde. Okay, it's a union of planes. Each triangle represents a plane. And you can see here all these numerated lines. Okay, this is actually C tilde. Okay, it's a line arrangement. C tilde is a line arrangement, you can see from here. Okay, and it gives us a lot of information later on about C itself. Later on, I will speak about line arrangements, but not as projections. So just in general, for you to know that also this thing, C tilde is also very interesting as itself because it's a line arrangement. Okay, so the question is what do we profit from the generation? It's also one of the methods that we use much before the algorithmic methods. It's because when we have G, we can draw the dual graph and the numbers representing the triangles are now the vertices of the edges in the dual graph. So it means that when I draw the dual graph, this is the dual graph. Okay, you see? This is the dual graph. Like this, and so on. Then each generator, for example, gamma 2, will be mapped to a transposition in the symmetric group Sn. So for example, if this triangle is alpha and this triangle is beta, then gamma 2 will be mapped to the transposition alpha beta. Okay, and in this way we can construct the dual graph, of course, after we get the fundamental group G. So you can see that the degeneration is very helpful in this situation. So you can see that we have some correspondence to the symmetric group, and it's nice to work with some groups that are well known. Now, I wrote in the title planar and non-planar degeneration, so some results about planar and non-planar degenerations before I go to the method. Just before
Meirav,
this,
may I ask you, may I just on previous slide, may I ask you the question?
yeah.
So you associate to every edge, you associate a permutation.
A
But
transposition, yes.
transposition, okay. But the question, if you consider the group generated, so on, is it possible, is it true that if you consider the composition of this transposition corresponding to different edges, so do they uh, correspond to something on the surface? Because you have a connected surface, as I understand. So it is not possible topologically to exchange these triangles, or maybe I don't well understand the,
Oh, you mean what is the connection to the surface?
yes, yes, yes.
This is what you mean. First of all, we don't need to go back to the surface. It's a very hard question, by the way. It's a very hard question to go back. We stay in this in the branch curve, and we can try to get the result about G, because we know that the G, the fundamental group G, if the surfaces in the same connected component in the moduli space, they have the same G. So I don't need to go back. If I need to go up, back to the surface S, it's a very hard question. Very, very hard question. I don't know
But but
how many
but
people.
look,
Hmm.
but if you consider no, so if you consider so you then consider the group generated but all those transpositions, yes?
Yes, but if there are some cycles, I will show later on. If there are some cycles, we need also to take some extra map that it's
Yes, I
not.
understand. Because if you just take the all no, each edge, you consider all permutations and you will get all the group, as I understand.
No. Not everything is a permutation. Yes, you are totally right. Because we need to consider that there are some cycles. So if there are some cycles, for example, this is the dual graph and there is some cycle, then it's totally a different story. It's a different
So,
story. And
so now I understand. So you put some additional relations and so.
yeah. There are some other constraints you will see later on. I just explained just for the beginning, so people will see the correspondent to the symmetry group. But later on, of course, I will show an example with a cycle or
Yes,
what
yes.
the general
Mhm.
group that we use in order to do it. And of course, there are other constraints.
Yes, yes, thank
Anyway.
you. I understand
Mm.
completely.
Okay, so yeah, so we see that there is some correspondence to the symmetry group. Okay, now let's continue, and I will show later on more information. So before I give some results on planar and non-planar degenerations that are very interesting, I just want to say that if G is too complicated, it might be because of two reasons: new types of singularities and high multiplicities of singularities. For example, in this picture, you can see that we took a complex torus and degenerated it. So this is a triangle. Okay, a complex torus can be degenerated to a triangle somehow by playing with the equation and so on. And we can take another complex torus. This is the second one. And it's a complex torus times a complex torus. It's a very complicated case. And you can see even in one of the points here that it's an intersection of 6 lines. And when we regenerate it, it's so complicated. It's only a local picture. So you can imagine how the curve C looks like. Very complicated. Anyway, um, so if the group G is too complicated, then we can compute also the G Galois. I denoted G Galois. This is the fundamental group of the Galois cover of S, of the surface. Please remember this notation along the talk. Now, also G Galois is an invariant of the surface, and sometimes maybe it's a bit easier to compute G Galois instead of G. Okay, so now some results on planar degenerations. First of all, we studied already planar degenerations about RK singularity. This is a joint work with Gong and Mo. Mo will be the next speaker after me. So you can see here that we degenerate a surface to a unique of an RK singularity, and we proved that the Giga is trivial for any K. So that was the first result. Now, we proceeded further, and we show some recent results with Gong and Mo, and we focus on some nice generalizations. Now, planar degenerations are maybe not so fascinating as non-planar degenerations, but we have enough constraints that they will be interesting. So the first generalization is the Galois covers of a union of zapatic surfaces of type RK. You just take two RK singularities and you glue them together. So except these RK singularities, you will have also these points in the middle, which are derived by the gluing, and they are also very complicated. But in general, after a very long work, we could show that the fundamental group G Galois is trivial. It means that the Galois covers of those zapatic surfaces are, with, of course, each one is one RK singularity, are simply connected. So this is the first generalization. And let me show you the second generalization. The second generalization is called deformations of zapatic surfaces and their Galois covers. So it's a joint work with Gong and Mo and with appendix by Kolar. We could prove that if we take surfaces that degenerate to, you see, one EK singularity, it is called EK singularity, such zapatic singularity, then the Galois covers of those surfaces are all simply connected of general type. The interesting thing is the following. It happens for n is bigger or equal to 4 and smaller or equal to 9. And for n is bigger than 9, such surfaces do not exist. So now I want to continue further to non-planar degeneration, where we use such singularities. Please look at this. So non-planar degenerations. First of all, you can see here that we have a tetrahedron. Okay, this is very simple case where we can identify 4 and 4, 3 and 3, and then 5 and 5, and we get a tetrahedron. And in this case, the Galois is trivial. And then we were very curious to know what happens, and we continued as follows. We took these two pieces and we glued them together to get degree 6 non-planar degeneration. And the G Galois is Z2 to the 4. So that was very interesting for us because this one was trivial and this one was Z2 to the 4. So we continued to this case, okay? We glued these two pieces together to get degree 8 non-planar degeneration, and we got that the G Galois is Metabelian group of order 2 to the 23. So still we cannot see generalization, and this is an open question to see what will happen till we get to E9, because this is the only possibility that it exists, yes, till E9. So, of course, we continue the work, and it's very interesting and very challenging. Now, some methodology. So, of course, in order to construct fundamental group, we need to use the Zariski-Van Kampen theorem. If C is a cuspidal curve of degree n, then the fundamental group G is generated by n generators, and we can have the following possible relations. So, if we have a branch point of a conic, okay, then we will have, and these are the elements, generators of the fundamental group, then we will have equality between them. Now, if we have a node, then we will have a commutation relation. If we have a cusp, okay, a cusp. Then we have some relation which I call it a triple relation. It means that ABA equals BAB, and so on. Okay, we might have other complicated singularities, and according to this, we can construct the relation. Of course, according to the braids. Now, to each presentation, we add the projective relation, which is the product of all the generators is the identity, and also some extra commutation relations that we add because of the following reason. This is S tilde, okay, the generated object of S. You can see, for example, that the ages 10 and 11 do not meet. But when we project S tilde onto CP squared to get C tilde, the line arrangement, they have to intersect. So we will have to add some extra commutations. So this is how we built the presentation of G. And now it's the time to use some softwares. So the first software, which was built with Sinichkin, takes the equations of the components of the curves and give us as an output the presentation of G. So we get the presentation with generators and relations. So you might ask me, okay, there are also other softwares, for example, SageMath, okay? But again, it depends on the resolution, what we want. With our software, we can also get the braids and the pictures of the braids, and we can get other extended information. So it's very good for us. Then, after we get the presentation G, we consider a special quotient, which is G with the squares of the generators. So we send this quotient into magma. Magma will give us an output, a simplified presentation of this quotient. Why do we need this quotient? Because of the following reason. We want to compute the fundamental group of the Galois cover of S. I told you that this is G Galois. And it is well known that G Galois is the kernel of the surjection from our quotient onto the asymmetric group Sn. I showed you the correspondence before. But you know, to compute kernel of a map, it's not easy. Also I remember my days as a student in linear algebra, and when they asked us to compute kernels of some maps, it was already too complicated. So also in such cases in the study. So it might happen that G Galois is too complicated also. So now we follow a joint work with Lawrence and Vishna. Lawrence and Vishna, the joint work, gives us some background in the beginning, and then I will give you the methodology. So first of all, if T is a planar graph, not necessarily simple, then we can construct the Artin group AT, where the generators of AT are the edges of the graph. And we might have the following relations. So if two edges meet in a vertex, then we have the so-called triple relation. If the edges are disjoint, then we have commutation, of course. And it might happen that in the dual graph, we will have two edges, for example, U1 and U2, okay, like this. So some doublings along the dual graph. And then these two generators constitute a free group of two generators. Okay, so this is just a quick background from that paper. And now, how do we use it? How do we use it? Pay attention, please. We take a specific quotient, AYT of AT. Okay, I cannot give you all the details because of shortening of the time. And from AYT, I can project AYT onto CYT, which is a special quotient of the well-known Coxeter group. And there was a proof that this quotient CYT is isomorphic to a semi-direct product of the symmetric group with very nice and interesting group, which is called FTN. The generators of FTN are called UIJ, and where N is the number of the vertices of T, and T is the number of the cycles of T. We need to pay attention to all this information. And now, the second software which was built gives us the output of the relations from our quotient in the language of this semi-direct product. And this is much easier to work with, okay, because SN is well known and we know how to work with all these elements in SN. For example, if this is the dual graph, you can see that we have here 8 vertices, so it means that in this case it will be S8, okay? And you can see that we have here also one cycle. Okay, so there are many parameters that we need when we use this software, many parameters that we need to check to see that which group it is, and then to get the relations in this language and to work with this. And now, till now, the algebraic surfaces part. And now I want to show you very quickly some information about algebraic curves that are also very interesting object by themselves. It's a classification of algebraic curves. So in the study, we use algebraic curves such as line arrangements and conic line arrangements. Now, we do it by finding or studying Zariski pairs. So this is very popular domain in these days. I want to show you two equivalent definitions of Zariski pairs, one by Shimada and one by Artal Bartolo. So Shimada says, I just copy-pasted their definitions. Shimada said that a pair of complex projective plane curves of the same degree is said to make a Zariski pair if the singularities have the same topological type. Of course, I will show a picture to explain this, while their embeddings in CP square are topologically different. And the equivalent definition is the following. Two curves C and D are members of a Zariski pair if two conditions. The first condition is that there is a degree-preserving bijection between the set of irreducible components of C and D. And there exist regular neighborhoods TC and TD, such that the pairs TC with the curve C and TD with the curve D are homeomorphic. And the homomorphism respects the bijection. And the second condition is that the pairs C with the embedding to CP square and D with the embedding to CP square are not homeomorphic. Now, let me show you very beautiful and interesting pictures. These are examples from Tokunaga's arrangements. So, Tokunaga works on these arrangements, and you can see that he took here degree 7 conic line arrangements. So look at the first pair. He took in each curve 2 conics and 3 lines. So it's a degree 7. Also on the right side, 3 conics and 2 conics and 3 lines. Now, what happens is the following. You take the line L3 and you start to spin it like a clock. Okay, you spin it in this direction, for example, okay, where this point is fixed. You see, this point is fixed. And then you can get on the right side the line L4. So he proved via diagonal covers that this is a Zariski pair. Now, let's go to the second pair. He took 3 conics and 1 line on both curves. And he could prove also via this method that this is a Zariski pair. Again, you take the line L1 and you spin it like a clock to get the line L2. Now, let's continue. Of course, I will return to these curves again in the next slide. Some results about Zariski pairs. So most of the known examples of Zariski pairs are pairs of irreducible curves, but we can try to find Zariski pairs among curves at the other extreme. And this is the interesting thing, to take union of curves of low degrees. Okay, this is the interesting thing to do. And there is so much work in this direction, many open questions. Now, some information about line arrangement. So the first Zariski pair of line arrangements were found by Rybnikov. So each arrangement in Rybnikov's example consists of 13 lines. It's very complicated, and 15 triple points. Okay? Very complicated, but Rybnikov is Rybnikov, and he could do it. Now, Nazir and Yoshinaga showed that there are no Zariski pairs of arrangement of 8 lines. Very important result. And later on, Ye showed that also there are no Zariski pair for line arrangement of with 9 lines. Also very strong result. And very important fact about Zariski pairs. Additional importance. It was shown by Randall that Zariski pairs of line arrangement cannot be in the same component of the moduli space. So this is also a powerful tool to study the moduli space of line arrangement. Now, I want to show you a result about line arrangement. It's partial results, of course, about 11 and 12 lines. These are some past works with Gong, Lieberman, Time, Teicher, Xu, and Wu. So we tried there to classify moduli spaces of, pay attention, arrangement of 11 lines with quintuple points and arrangement of 12 lines with sextic points. Because if you take other cases, it splits to hundreds of them. It is very complicated. There are many open questions there if you are interested in this, in work, in line arrangements. So we took these cases, which are relatively simpler than the other ones, okay? Because you can control the amount of the cases, let's say. And we showed that the moduli spaces of such arrangement can consist of more than 2 connected components. You can see here that there is a lot of combinatorial work of how to do this. I make the picture larger, especially for you, so you can see that, for example, if the line 11 is fixed, then you try to think, where should I put the line 10? And then you can split yourself to so many subcases. So it's very complicated, a lot of combinatorics and computations, how to do this. But then also you get some potential Zariski pairs. Okay, because you are not sure, it depends again on the method that you use. Again, here, we still didn't do the computations of the fundamental groups because it's too complicated and it's also some open question. And when you have the fundamental group, then maybe you can derive the result. Now, conic arrangements, there is also nice result about conic arrangement. Namba and Tushihashi, they also prove that there is a Zariski pair with these 2 curves, as you can see here. Each curve consists of 4 conics, so it's a degree 8 conic arrangements. And then very quickly about conic line arrangement, some results. It is well known by Dektiarev that there are no Zariski pairs of degree smaller or equal to 5. Okay, and so then we tried to find some information about degree 6 conic line arrangement, but still it's an open question. we work on it. It's still an open question about degree 6 conic line arrangement. And again, you can see Tokunaga's arrangements of degree 7. He could prove by diagonal covers. I remind you, for example, this picture from the previous slide. He could prove the Zariski pairs. Okay, now Banai, Tokunaga, and Yorisaki. This is very recent work from Japan. They studied the embedded topology of certain conic line arrangement of degree 7. And they determine the number of connected components of conic line arrangements. You can see very interesting in the pictures that they also correspond some conic line arrangement to others because they are the generations of each other. So usually we worked on the generation on the level of surfaces, but they also started to work on the generations for one curve to another. And so it splits also to many, many cases according to the generation classification. And there is also very nice advances by Banai, Gurvil, Bal, and Shiran. As you can see here, they proceeded already to degree 9 conic line arrangement, but again, it's very complicated. So what they did is that they took one conic and 7 lines, and they played with the lines, they spinned them, and they could prove that there are some Zariski pairs in degree 9 conic line arrangements. And now the rule to find Zariski pair is the following. So this is the rule that I wanted to show you toward almost the end of my talk, that if two curves, say B1 and B2, have the same combinatorial type and different fundamental groups, then they form a Zariski pair. But you must write a Zariski pair with non-isomorphic fundamental groups. And this is also very important. If you have a Zariski pair, I mean, if you succeeded to prove a Zariski pair, okay, via another method, let's say, then it does not imply that we have Zariski pair with non-isomorphic fundamental groups. So you need to be careful to which direction you go. So this is all about, okay, this slide. And very quick example, you can see that it's very similar to Tokunaga's arrangement. We just added a line to get degree 8 conic line arrangement. This is a joint work with Schwarz, Sinichkin, Tan, and Tokunaga. He joined us to this work, and we could prove via fundamental groups that these two curves are a Zariski pair of degree 8 conic line arrangement. And of course, on that work, we took the degree 7 Zariski pairs that were introduced by Tokunaga in 2014. The pictures that I showed you before, I just summarized them here. And we also proved via fundamental group that these are Zariski pair. He proved them already, yes, via diagonal covers, but we did it already via fundamental groups. That was very interesting and very challenging because we had to use some Coxeter groups and properties of well-known groups. Really, very, very interesting and challenging work. And the last slide is that there is also some direction of study on some families of plane curves using some symmetries. This is a joint work with Kuma, Roy, and Sinichkin, and it is called the fundamental group of highly symmetrical curves and Fermat line arrangements. So we took some Fermat line arrangement. So this is the equation, okay, in general of the family of Fermat arrangements, and we used some symmetries in the family to find the fundamental group G. So I think that it's also nice to take some families of groups and to try to find generalization about the fundamental groups, and then to compare to other families and to see what we can derive. Maybe there is some degenerations or something like this. And what is interesting in the Fermat, the fundamental group G is a semi-direct product of a free group with n generators, because of this n, you see, and with a special group derived by the symmetries on the curve C. So that was very interesting work. You are welcome to look on this work. And that's it. Thank you very much for this for this opportunity and amazing platform to give me the possibility to talk. Thank you so much. You have a great conference. Thank you.
Thank you very much, Meirav. Thank you. Let us send the speaker. Thank you.